to discuss. I'm going to give you not even a transfer reaction 101, but we'll discuss a few things that we need to at least understand for the application of transfer reactions to the question of pairing. And then we'll discuss some other aspects which are perhaps more contemporary today, of things that are still not answered well. And we'll discuss a little bit about neutron-proton pairing. This will be mainly an experimental discussion for those of you who are sort of more inclined to the experiment. I'll discuss some of the ideas there, and then we conclude with some other aspect of pairing and hopefully summary and some conclusions. So let me start with the first one was in discussing the residual interaction. I show you this plot which indicates that the residual interaction seems to decrease with the A of the system, and the argument that I made was that of a volume effect, because the volume is R cubed, and for most of the nuclei near stability line and not too exotic, that's case like 1 over A, and there were some questions raised where I don't believe you and things like that, but so I try to convey to you that there's some assumptions. This is one limit that you would expect, and it's not completely unreasonable. Again, like in anything that we discuss, there are particular details. If you go to a particular nucleus, which particular orbits, that may not be the case. Why is that? Well, I think it's simple. That's the matrix element, two-body matrix element written in terms of the wave function, and I'm going to take a very simple wave function, namely one that is constant in the volume and zero otherwise. That, of course, already is an approximation, but nevertheless, not a bad one. In fact, all the you may have heard during these talks things like Bife units estimates and things like that for transition probabilities, which are based on a very simple wave function like this. And then, of course, the condition is the normalization to 1, and then you realize immediately that that n there has to be 1 over the square root of the volume. And now, if you assume that you have a short-range interaction, say like a delta function of time, then you realize that this integral here for, say, particle 2 reduces to the value of n squared and V0, because this applies to be only when they are on top of each other, and therefore the integral now of this gives you 1, and V12 then becomes V0 over the volume, which again, in some nuclei, we will use this later actually, and you will see the little detail there. It has to be the volume. Most of the nucleus that A, but in some others it may not, particular halon. So this gives you sort of an idea why it should decrease with the size. And the argument is because it's a short range, and then you ask yourself how many times they are close to each other, and if the volume is large, that probability will be small. So that's one of the odds and ends. The second was related to the Migdal formula. Some of you quickly realize that the limit of the quench pairing, or when the value of x becomes very small, means that pairing is not enough to overcome the single particle degree of freedom, will give you the rigid moment of inertia. And the question was, how can I do that in a nucleus that is spherical? And that was a very good question, because nuclei which are spherical do not like to rotate very much. But it was hard for us to see that there were some yellow points there in that corner, and I said those corresponds to a particular case, and here now, since you are experts, I don't have to explain anything. This is the Nielsen version of an harmonic oscillator on the left, and this was the cartoon that I was trying to draw there. You see the spherical shells, very pronounced. This, of course, is not the real shells up beyond calcium 40, because this is an harmonic oscillator, no spin orbit splitting. But it illustrates the fact that for particular ratios, in particular this one of 2 to 1, which is the ratio of the axis in a deformed system, other gaps develop. And this is like that in a way. It's a very robust shell closure, with the difference that now that nucleus is deformed. In fact, such especially deformed that we have called those super deformed. And now when you do a more realistic calculation, in this case it's based on a Wood-Saxon potential and not the Nielsen modified harmonic oscillator, you see that that structure continues to persist, and there are important gaps that develop at this last deformation, equally important as the spherical shell. So, for example, I couldn't resist to show you a beautiful rotational spectrum. Have you seen one during these lectures? Well, I don't think it's as good as this. That's done with gamma sphere. Look at that rotational spectrum. This is dysprosium 152, the super deformed band. The picket fence, it goes almost to spin 80 here. So it's a beautiful sequence, and if you look at the moment of inertia of this band, it's very close to the rigid value that you would expect for dysprosium 152. And so that is the key signature of the rotation and the moment of inertia. And then a final plot related to this is the fact that now if you do a systematics of what the deformation may be across the periodic table, you can, in a simple formula, that the Q naught, so the quadruple moment related to, my apologies, in this case, this X is the ratio B over A, so the axis. And you can determine that the deformation as expressed by this quantity, you see it also goes down with size. That will be the Nielsen deformation. You have a system that is unstable with deformation and is driven by the effect of the potential. It should go down. However, if you have this special harmonic oscillator or Nielsen gaps which occur at particular aspect ratios of that, those are like lead to red. They are special doubly closed magic super deformed, and that deformation doesn't really change much with the size. And you see uranium, for example, has a similar deformation in the shape isomer as dysprosium 152, because it's kept at the value of 2 to 1. It doesn't like to drift around, it just keeps there, and that I think is very important, and was the key points that Bohr and Motteson made when we were studying this. So, okay, this is the one of the other ends that sort of ties up with the Migdal formula and that aspect of pairing. Now, as we learn a little more during the afternoon session, the fact that these are closed shell, that doesn't mean that pairing doesn't play a role, because now pairing degree of freedom in this nuclei, like in lead 208, is in the form of a pairing vibration, as we saw during the activities when we solved the problem. Okay. So, I'm sure that you've seen this plot. This is another odds and ends. Before we go into transfer reaction, you saw that plot probably during the lectures of Professor Pietrala, which is this sort of shape transition, and the transitional nuclei and this so-called critical point when you go from a spherical system form and then the nucleus in this intermediate region doesn't really know what to do, and the question is how do you describe that? And then you can take a spherical picture and do some kind of expansion along that. You can take this one and do some kind of approximation from this side, then Yakello, and then experimentally determined by Rick Caston and others. You can actually approximate this potential and plug that into the so-called collective Hamiltonian. That is a classical, if you like, it's a quantum collective description of the nucleus in terms of the vibrations and rotations. And this potential that drives the dynamics, you can approximate like a parabola here, and then you will get a vibrator. You can put a potential like that, then you guess the rotor. And so Yakello said, why don't approximate this with a square well, which is sort of a representative of that transitional nucleus, and what do you get? And actually, you probably discussed that in detail. What you get is so-called critical point descriptions, and I'll show you a little later what that means. So, but actually, with the analogy that we have with the pairing and shape transitions, there is an equally collective equation that you can write for the dynamics of the pairing gap, in this case represented by this quantity alpha, which is the deformation of the pair field. So here is not the shape of the nucleus, but rather whether the pairing is zero or not, and how it fluctuates. And that potential V, we saw some examples the other day, can be plugged into that equation. So what we did was to follow Yakello's approach and solve this Hamiltonian in the actual approximation of a square wave. Now you discuss it in length, I guess, the solutions of this Hamiltonian and the so famous Caston triangle there, and actually you saw the discussion of X5 and E5, I believe in detail. And actually you can convince yourself that there is a similar problem here, and what X5 and E5, that's because it's a Euclidean group. For us in pairing there is only one gauge angle and the deformation of the pair deformation. So if you imagine it's a two-dimensional problem, you have an ellipse, and then how do you rotate that and define the position that's given by the so-called angle phi instead of the Euler angle. So that translates into a U2, SO3, and in the middle the E2. So the solution that we discovered was E2. This is the sort of the normal system, and this is the rotational in pairing. We are a little bit more modest than Rick, and so we have the so-called CMFK segment. How about that? So the idea actually is very simple. You take that equation. Those of you who are mathematically inclined can look a little bit more. There is a copy, a PDF file of that analysis we did with the package you got yesterday. And actually it's a simple problem, because if we could do it with rod, it means that it's not too complicated, you see. And so essentially if you put alpha squared, a potential like that, and you plug it into this equation, you get the energy goes linear on the mass, like we showed solving the two-level problem. If you put a potential which is sort of like a deformed potential here, you indeed show, and you can see that in the paper. I'll show you a little bit the results here. You take this sort of flat potential, replace it like Yakello did by a wall, and then actually the equation has an interesting solution, which is that of a Bessel function. And so you solve that equation. The boundary condition, of course, because we have an infinite shell, is that the wave function stops at that point, it has to be zero at that point, and therefore those conditions determine that the solution can be cast with a quantum number psi and this m, which is nothing but the number of pairs that you have. And you can actually obtain the associated eigenvalues, which depends on the zeros of this Bessel function. And then you can go to Wolfram Mathematica or any table that tell you what those are, and that's we did. And when you do that, and then you say, well, I'm going to look at the energies of this system by looking at these values, then you get those here. You can confirm that if you want. And then you see nicely that indeed, in the vibrator limit, linear, the rotor is a parabola, and at the critical point is, of course, something in between. The interesting thing is how that this compares with the data, because that may not be close to the data. But actually, that is the solution determined by this sort of flat potential. And when you do that, and that we did for lead 208, which of course was the case that I introduced you to, that was done by the seminal work of Mottelson and Bohr, the interesting thing is that you indeed see that the data in lead 208 looks very close to the critical point, which is already an indication, as we were arguing yesterday when we determined the order of magnitude of the X control parameter. Nuclei are very close to the transition point. As soon as you remove or add a few particles to the closed shell, the system becomes superconductors. Now, this is not only a feature in the lead 208 region. There are other, of course, regions, and for example, I'll show you here some bands near other closed shells, Nico 56, Tin 132, and you can see here that they cluster near the critical point. And of course, that gives you, in the same way that the X5 and E5, a closer description of those nuclei in terms of Penning correlation. Now, if you want to use that to describe transfer reactions, as we will see later, this is a better approximation. Now, of course, you can start, like we say, from the vibrator, perhaps will be the best way to do it, because the rotor seems a little far away. So you could start with the vibrator, and in fact, that's the analysis that Mottelson did in describing the Nobel lecture here. But then, see what he says. Large anharmonicities in the spectrum must be accounted for, because it's not linear, you saw. It's a little bit above linear, and therefore it cannot be a pure phonon. It has to have anharmonicities. And then if you go actually to page 646 of the Bible, you will find there that they add a term. So you have a phonon, and then you have a term that involves interaction between the phonons, and then they actually adjust this parameter, which is an harmonic term, to get you 700 kV in order to reproduce that shape in that spectrum. Well, guess what? If we take our solution and you get and plug the numbers from the Bessel functions, we get 800 kV. So that's very close to the data. So, you know, it's a better approximation of that phenomenon, just by taking into account the fact that the potential is not either a vibrate, a parabola, or a parabola centered around the deformation. So I thought that this was something that was worth discussing a little further. And we will, you can now actually, since you have the code, and you can play with that at your leisure and whatever you want, if you are interested in one boring evening. You could actually run the code and find out that the 2J shell, which is done here with the solid lines, lies very close to the red points, which is our collective solution when the parameter x is there between 102 and 103. So if you run the code, put x and then you look at the energy as a function of the mass that we did yesterday, you will find that it lies on top of those points, because this figure was derived from the two shell. So with this, I think I would like to close sort of the aspect of the pairing phase transition, but address an important question before we go to plunger. And the question is, we are all happy, it seems like in a phenomenological or a schematic description based on empirical data and some ideas of some simple models, pairing seems to be playing an important role, and some of the properties like moment of inertia, binding energies, and energy spectra seem to follow. We saw also examples from Rick on deformed systems, and actually because in the Nielsen model you have realized that as soon as you move away from the closed shell, the level density increases dramatically. Therefore, the fact that the level density increases means that the delta energy between levels is not much smaller, and therefore pairing thrives in those conditions, and almost as a guarantee, except on those which are super deformed. Most of these deformed systems are superconductors, or BCS. The vibrational degree of freedom on pairing applies only to double closed shells nuclei, which are either spherical or the super deformed region. But the key question that I would like you to ask yourself is, where does pairing come from? Why is it that the nuclei... now, of course, at some point we will have to wait for an initial calculation that takes into account the quark degree of freedom, so some kind of lattice calculations that show you that from the quark degrees of freedom we get the nuclear force that we know. I'm not too optimistic of that now. There are calculations. I'm just a little bit. So we know, what will we know from the nuclear interaction that we can understand? And the basic question that people have measured at the beginning and studied it very much in detail is the so-called scattering length, which is the scattering of neutron-neutron, proton-proton, or proton-neutron, for which we see that at very low energies, or in this particular case, the channel is described by L, so S is equal 0, and then you have angular momentum 0, so this is referred to as S10. The fact that this phase shift is large and positive means that this is very, very attractive. Yes?
Is there any reason why the plot is going left?
The only reason it's going left is because I wanted to align it with this region of low density, because actually the next point is the following. This is very attractive at low energies, but then when the energy increases, you know there is a hard core interaction and even becomes repulsive. So at low energy, if you like a neutron-neutron or a neutron-proton or a proton-proton, they are strongly attractive. Now, where will that happen in the nucleus? To have low velocity, where do you think the nucleons are moving at low velocity?
In the higher orbit, means L is high. When the orbital angular momentum, when the orbital is a little bigger, then the nucleon will move slower. And this L is equal to 2 or 3 or more than that.
Yes, but also, I mean, if you imagine a pendulum, and there you have a kinetic energy term and the potential energy, and then you swing the pendulum, where is the pendulum moving at very low velocity?
In the extreme
At the extremes. Okay, so here Here the equivalent of the limits of the pendulum is the size of the potential, and then when the nucleon approaches the surface, turns around very slowly. And if you look, that's where the two nucleons will come at low velocity. So that's one of the arguments that people have made to convince yourself that pairing is a surface phenomenon. Now there is a speculation that there is a volume term, and people, that's one of the subjects of discussion these days about pairing, the nature of pairing correlation. But at this level, I try to convey to you that it's not a surprise that near the surface, where the density becomes lower and the velocity becomes small, then a Cooper pair light can form because they like to attract each other in a j=0 state. Now, if that were the case, then in a simple sort of cartoonish paper, I can take a very basic NN interaction, say the argon potential or any other basic potential force, and calculate what that matrix element will be. And when you do that, for example, you find yourself that the gap that you will calculate with that strength, it's only half of the experimental gap. So something is not completely there. So although the nuclear force at these conditions is already attractive and would favor pairing, that pairing is not enough to give you the experimental data. So what is there that two nucleons in vacuum don't have that may give you the extra? So if you go to tin, this is the case of tin case, and we will look at this afternoon. So, I mean, you have two nucleons there, but in the presence of others. So it's not that they are in vacuum. They are in a medium of other nucleons. And these guys interact and they talk to each other. And actually, early on, George Bergs pointed out that, contrary to what I said early on at the beginning, that the closed core cannot, probably is quite inert. It's not completely so. And actually, you can imagine that a nucleon comes and excites a particle Hopf pair from that medium, and actually this effect, as he says here, is attractive for T=1 low J states. And actually, you can see that, and this is really amazing. I like it a lot because, you know, we talked about the surface, and so the nucleon is near the surface, and that's where the vibration happens. Okay, I mean the surface vibrates. So actually, what happens in a collective picture, that one nucleon, say a neutron, excites the vibration of the core, and some other neutron, which is somewhere else, picks up that vibration, and it's like if they attract each other. Well, this is exactly the reason why there is superconductivity in solid state, because the electrons repel each other. So how could they get superconductivity? And it's because the electrons get attracted by the phonon lattice, the phonon produced by the lattice in the superconductor. So this is a one-to-one analogy. Again, the same underlying physics that applies in a similar way in the nucleus. Of course, more complicated because in the electrons case, the phonon are made by the lattice, the electrons are other entities. Here, everybody is sort of making everything. So the phonons are made by the nucleons and the nucleus. So it's a little bit more complex, yet more rich a system. But it's somewhat amazing, the analogy. And then I wouldn't be a surprise, because I'm already talking, that when you do that and you call it the renormalized pairing, and so yeah, that renormalized pairing, and you have a reference there that you can look by Francisco Barranco. You take the Bayer interaction and then you take into account this renormalization effect, and lo and behold, you get very close to the experimental limit. And actually you can prove within some hand-waving arguments and some estimates that this is about half of the Bohr-Mottelson gap that we discussed in the lecture of yesterday. And there will be a problem this afternoon where I propose to you to estimate actually the pairing constant from helium-6, and then the question will be what would you get? And so the idea will be along these lines, but this is a very nice feature of pairing correlation. Now, of course, for those of you who are studying and may be interested in pairing, there are other questions. Three-body forces, how does three-body forces influence pairing? That's a subject of topic interested. Maybe you guys will give contributions on that. And people say actually that the three-body force will bring this down a little bit. And so yes, there is still only a lot of open questions that I hope by the end of today's lecture I will try to convey to you. So transfer reactions. So we start here with the topic of the second lecture, and it's, again, I mean, when we have a few other schools that you may have participated or I was part of it, transfer reaction was already on itself 2 or 3 lectures. So in 10 minutes I cannot even start. But I'll tell you a little bit, a few things that perhaps is not difficult to understand that will allow us to then discuss the particular influence that this tool can help us answer pairing. So as we discussed during the topic of this school, I think our idea is always to try to look at the elementary modes of excitations, and then we have approaches where we look at heavier systems, lighter systems. We also showed yesterday, and Rick, with the Nielsen model, that we can influence the behavior and learn about the force, learn about the properties by making the nucleus rotate. And we are also looking in isospin. And I will mention very briefly at the end, because this is one of the topics also that you may get engaged with, still a lot of interesting things with temperature. And I guess it's not a surprise that transfer reactions have been a major tool that people have used in the inception of accelerators to study single particle and correlations, and I'll show you a little bit of why. I'll try to convince you why that is. And now, actually, as we have developed exotic beams, there was some kind of a time where transfer reactions went out of fashion and people was more interested in gamma ray spectroscopy and high-speed phenomena. But as exotic beams were developed, there is a renaissance of transfer reactions, but with some twist on it, because now the beam is what it used to be the target, and new techniques have to be developed, and I'll try to show you some example with the neutron-proton pair. Why that is? Why is it that pairing, that transfer reactions are so important? Perhaps before we doing that, I'll show you a recent example. This was a holy grail in the field for some time, and this has been published in Nature from the work of Kate Jones and collaborators at Oak Ridge, where they did tin-132, DP. So they transferred a nucleon into tin-132 to learn about the levels of tin-133, which is one of the holy grails of this doubly closed shell nucleus that has many interesting applications as you approach the weakly bound system. And here again, the beam was tin-132 and the target was a deuterium target, and that poses some questions, and this is the spectrum that you get that allows you to determine the sequence of the levels in terms of energies, but moreover the nature of the level by measuring the angular momentum and something that goes by the name of spectroscopic factors that we'll address in the next slide. So why is that? Well, actually Butler already, as I said, in the 50s, noticed that if you were to assume a direct process, and just because of angular momentum conservation, the angular distribution in a reaction like dP, for example, where you come with a deuteron, you dump a neutron and you detect the proton. The angular distribution of the proton carries information about the nature of the transfer process, and actually if you measure the angular distribution, and this is what we do in experiment, you can determine what's an L equals 0 transfer, L equals 1, L equals 2, etc. So that's a very nice tool, because now you can say, it was an S orbit, or it was a D orbit, or an F orbit, like K did. And then the other thing is that within some approximation of the problem, you can decouple the reaction part from the structure part. The structure goes into something that is called spectroscopic factor S, which depends on the nature of the orbit, LSJ, and the structure of the nucleus, and that's very important. And then a reaction part, which is usually done in some approximation too. The most popular one is the distorted waves approximation, and we will hopefully have time this afternoon to do some, or expose you, let me put it that way, expose you to one of the most famous codes. It's called DWAC, that allows you to calculate this. Those who are in the experimental side will measure this, and then we determine some spectroscopic factor that those who are in the theoretical side will provide, and see if the structure agrees with the data or not. So essentially what we are doing by looking at this is an overlap between the initial and the final state, and that's indicated in the cartoon way in this plot. I mean, you imagine here, this is the deuteron coming in, and then the neutron gets dumped into the core A, and the proton is detected. And then the operator in question here is very simple. It's A plus to A plus 1. So you ask yourself, how is it that A plus 1 looks as A dagger on A? If it's a single particle, for example, then it will be very close to 1, that operator, and your spectroscopic factor will be large. But if the system is strongly mixed, then that will be fragmented among many states. The spectroscopic factor could be very small. And therefore, in this particular case, because we are dumping a neutron in the system, and in the language that we learned yesterday about the BCS, we are asking about vacancies. If the state is occupied, you cannot put it there, of course. You have to have a whole light of state to be coming in. If you now do the reverse, you can actually start with the nucleus, the target A, and remove a neutron from there, and go to A minus 1 again. What is the overlap of this with that? Again, it will tell us about the structure. And in this particular case, this reaction proves the particle nature of the particles that are there. If the particle is not there, then you will not get it out. So a combination of these two will allow you to learn about the single particle structure, or more appropriately, if you like, quasi-particle structure, which I try to sort of summarize in this cartoon. This is the Fermi surface that we introduced yesterday. If it were a completely single particle, it would be sharp. This is not true in nuclei, because we know there is some pairing, at least pairing we know is mirroring the Fermi surface. There obviously some other residual interactions will do a similar thing, but if it were only pairing, this is what we get. And then we have the occupation D and U. They add to 1, so they have this behavior. So if I do a DP reaction from nucleus A, I'm going into the population of those states. If that state is completely empty, then I will get the probability will be 1, but some of them are sometimes not empty because they are post particles and holes, and I will get something which is less than 1. The important thing is that we conserve the nucleons there. We cannot just arbitrarily have a number, and there is a sum rule that goes by the name of Machiavelli in French, which tells me that if I add or I remove, I should add to the total number of particles that I have in that level. I cannot. And so if I sum all the strength that I associate with that level, I should be able to recover the French rule. And sometimes this is used in cases where you calibrate the reaction. It's not done completely in absolute terms, but it's done relative. But once you know you have all the strength, you sum and then you recover to Z plus 1. It can thus be done. And I show you here a nice example because we've been looking at the calcium isotopes richer than calcium-48, but there was a beautiful set of experiments done with polarized deuteron. That's the reference, by the way, on calcium-48. They have done earlier calcium-40, so you can look at that reference. But look at that nice plot. By doing DP, they actually determine the Fermi surface. These are the empty levels. Of course, this is the occupation. That doesn't mean, actually that's measured with very precision because these are actually have spectroscopic factor close to 1. Then by taking the difference, you know how much they are there. And look, calcium-48, calcium-40, similar analysis. Obviously, we are not talking about the same orbits here because these are the SD, this is the F, that's the F7 half. This is not surprising, you know, the F7 half should be completely full in calcium-48. So if you try to make a particle there, you will not get it. So what can you conclude for that, if you see that, in terms of the Fermi circuit? What can you conclude? What would you say about calcium-48 and calcium?
Fermi surface is more diffuse in 40 calcium.
Exactly. So from that point of view, one would conclude, and from what we learned in the lectures yesterday, that the diffusion of this Fermi surface is introduced by the effect of the pairing gap. And therefore, calcium-48 is more robust to perturbations from the pairing and generate a gap which is smaller than in calcium-40. And therefore, there is more mixing in calcium-40, so this would be a nice course, if you like, if I were to do shell model calculation than if I take calcium-40. So that, you see, you can do. So single particle transfer already tells you not only about the sequence of levels, but whether those levels are really single particle or quasi-particle, or maybe they are mixed by other reasons. But in this particular case, you see a nice result.
So you now we are considering DP.
Yeah, this particular experiment is DP.
So,
But actually even more so, let me add, polarized DP. So
Okay,
they even have more information about that.
okay, now so we add 1 neutron into the calcium-40 and calcium-48.
Correct.
So I think in the case of calcium-40, 1 neutron, added neutron, stay F7 half orbit. So there is a gap of 28. So, and I mean, in the case of calcium-48, the added neutron in the PF shell. So
Correct.
the spacing is more smaller. I mean, between single particle energies.
Yeah, that would be the naive picture that I would say,
Yeah.
but
So, but it the result shows the opposite trend.
yeah, the gap here, which is between the S and the F7 half here, is less effective than the gap between the F7 half and the rest of the FP. And in fact, the calculations agree very well with that. The shell model calculation.
Both of them are like magic in proton and neutron number.
Yes, of course, in
Yeah.
a simple harmonic oscillator picture, they
But we can say this calcium 40 is like different, they have N and Z. They are in the same shell, neutron, proton, so they interact as well.
well, actually, in calcium 40, somebody mentioned the other day when we are discussing super deformed bands, there is a strong possibility of making deformed states by breaking the core in calcium 40, and that's what the ground state, or the ground state of calcium 40 is actually a mixture of a shell model like nucleus plus deformed. So that's why this surface is not sharp as it is in calcium 48, and it is because of the somewhat cooperative effect of the neutrons and protons in deforming. Okay, so that's there. Let me show you an example, because sometimes it's not only the structure aspects that we are interested, but as we said at the beginning, and it's a theme that I'm sure that is recurrent during this school, there are applications for which nuclear structure is extremely important. And neutrino double beta decays is one of those, because as you know, both worldwide there are efforts to try to pin down whether the neutrino is a Majorana particle or not. And one of the unique experiments is in our camp, double beta decay. And for that particular case, the transformation goes, in this particular case, I'm going to mention the germanium, because germanium is part of the Gerda project in Europe, is part of the Majorana project in the US. And why is it so good? It's because germanium is such a good detector for gamma rays, that the resolution that you get for this decay is unprecedented. So that's why people have picked germanium. And here the reason is that you will go from here to there in a double beta decay with emission or not emission of the neutrino, depending on the nature of that neutrino. And actually, if you measure that lifetime from here to there, you can conclude about the neutrino mass, but there is a nuclear matrix element input that you need to put. And it could be that if that matrix element is not very good, you may not observe anything, even if it's there. And therefore it becomes extremely important, either if you can always argue, if you see something, it doesn't matter, okay, it will be a Nobel Prize. But I think at some point we will need to provide that matrix element. And although we, in our type of experiments, cannot probe that matrix element directly, obviously you realize that if you're going to go from here to there, there must be a nuclear overlap between these two guys that can depend on the wave functions. And that's where transfer reactions come into play, because I can learn about the nature of this guy and the nature of that guy and see whether they agree with some model that then I can use to calculate the double beta decay matrix element. And therefore, that's what John Schiffer and Sean Freeman did. Actually, they did a series of experiments at Yale, because that facility was a unique position, because it had the tandem, provide beautiful light beams, and the instrumentation here, nice spectrometer to do the reaction to detect the charged particles, and that's what they did. They did a series of experiments. Again, as you see, they did DP and PD because they are complementary and they can apply those sum rules for each of the levels that they look in germanium. Why did they pick alpha helium-3 and helium-3 alpha? That's a detail that will take also some time to discuss. I told you that the kinematics determines the angular momentum transfer, and if it is a high speed transfer, then usually that's not particularly the case because the Q value is not optimum. Then you have to use another reaction, in this case generated by alpha helium 3, which the Q value helps you because it's a large Q value mismatch that is compensated by the transfer of angular momentum. But again, that will take a lecture on its own. But at least I give you the flavor, nice spectrum in the spectrometer there. The reference for this is here if you want to see. They can now look at all the excitations, and actually you can, oops, sorry. That's an example that John provided me. If you were to do DP and run the WBA calculation, you see indeed that it is very sensitive to the L for this particular case. So by looking at the angular distribution, then you can tell which level you are talking about. You measure the cross-section, you determine the spectroscopic factor of the occupation probabilities as we determined early, and this is what you get. So the levels in questions are here, the P's, the F1 and the G9, and this is what they determine in that sequence of the nuclei which are involved in this square that relates the vertices of the double beta decay. And you can see actually that if you look at the difference in occupation number between these two partners, which are actually the relevant ones for the initial and the final state, and you compare with one of the state-of-the-art calculations done in terms of an RPA type of a vibrational type of structure, the agreement is not very good. So there is much need for improving the calculation, and many theoreticians are now working hard on this problem. It will appear that the nature of this makes that as they said, that the Fermi surface is much more diffuse than what they expect from the RPA, indicating that indeed pairing correlations in both initial and final states are very important and make that the Fermi surface is diffuse. Now, of course, this is not direct measure of the matrix element. I tell you a little bit about the structure of those nuclei, and the consequence, of course, remain to be seen. But these have initiated some revision of the models, including Franco Iacchello now strongly involved in the determination of this matrix, given the importance of the problem.
Augusto, did they compare with shell model calculations?
Not in this paper, and I know, but I know John was working with Alfredo, and but I don't know if somebody could. Maybe some of you can.
Interested in doing this.
With that, you can do this with our model.
I don't know. This is a difficult.
That's right.
No, our model is too big. I mean, you cannot do this. But with a shell model, a good shell model.
I believe yes, and I think Alfredo has good results. Okay, so we still have some 15 minutes before the break or so. So let me now go back to this analogy that we have used already several times, and you have probably analyzed during these 3 weeks that another measure and observable that can inform us about the collectivity of a shape collectivity is the so-called transition rates, particularly for the formed quadrupole systems. That goes under the name of a V of E2 between the two spin I and spin I plus 2. In particular, yesterday we were discussing the 2 plus to 0 plus. And usually the larger this number is compared to some kind of single particle limit, the more enhanced the collectivity is. And now when you go to our system, which is again the pairing system, the equivalent for that, this deformation here is this matrix element, which is the two-particle creation operator. So, which is exactly what we want to study, and therefore it is not a surprise that because the nature of this operator is essentially creating two nucleons in nucleon A, if you like. I can go to nucleon B, to nucleus B, and if I study the cross section for 2n transfer, then I go from n plus 2, and I actually have a way of measuring that operator. So that's where transfer reactions come into play, but in this time two nucleon amplitudes. And again, in a similar cartoon there, for example, you come in here with a triton beam, and you dump two neutrons in nucleus A, and this process is determined by this transfer operator, which actually you can see is exactly the one that is involved in the pairing there. So if I would measure these cross sections, then I will have an equivalent of the B of E2 when I compare these transfer reactions with a single particle case. This will be the equivalent of comparing the B of E2 with the Weisskopf units for electromagnetic transition. And actually, there is a little bit of a difference here, as we will see in the problems and the exercises this afternoon. Contrary to a single particle transfer, where the structure part and the reaction part is given just by the spectroscopic factor, this transfer actually contribute coherently, and is not a simple product. There is a coherent sum that in some approximations can also be separated and result in a constructive interference that is the key element for measuring the pairing gap, and we will analyze that in the problems and activities this afternoon. This was obviously realized immediately by many, particularly Yoshida-san was the first one to realize that, and in the early 60s. And as John Schiffer likes to quote, this was the key element that people finally was convinced that indeed this pairing correlation at a BCS was indeed the mechanism behind the properties of pairing. And there is, as I say here, many interesting literature where you can go back, and this obviously is a nice paper, actually quite simple, even non-expert can understand, but essentially convince people that pairing was a mechanism. You know, you realize this is not too far from when Bohr-Mortensen and Pines came up with the idea of BCS for the nucleus. We are going to try to convince ourselves that that is indeed the case by, again, looking at some toy models. I think toy models are not a reality, but they capture the main ingredient and they give you some general arguments of why this happened. And at least when you analyze the data, of course, you will have to do a more realistic calculation, but sometimes the details are hidden in those big calculations, and the simple model allows you to understand. So we will show this afternoon, and I leave that for the activities and problems, that if you are near closed shell, we said yesterday, of course, lead to A, there is no much pairing. But pairing is present in the form of a phonon, and when you think in terms of phonons, the collectivity increases with the number of phonons. So the V of E2 of the second phonon to the first phonon is larger than the first phonon to the ground state. And here is the same. The transverse cross-section for the second phonon to the first phonon should be larger than that of the by a factor of 2, which is the number of phonons. So near the closed shell, I will expect that the increase of cross-section should go linearly with the number of phonons, and we will prove that both by hand, by solving a real simple Tory model, and then a little bit more complicated with the codes that we developed yesterday, and you will convince yourself that that's indeed the case.
Not yesterday.
Sorry.
He's calendar challenged.
I am. Tuesday. And we will also show that even in the case of the phonon, the pairing is enough to enhance that over a single part. Because those components in the phonon act coherently and they enhance the cross-section over if it were just a single two particles in a single J. And the order of the enhancement is the degeneracy. If you have, say, 3-4 levels that contribute to that, it will be enhanced by that number. Now you add particles, and as we show, at some point, then you become superfluid, and there the enhancement is even large. It does not change anymore once you are in the limit of superfluid. All the superfluid, as we saw it yesterday, look really the same. They are boring to some extent. Everything is washed out, and you see a similar effect in all. But the enhancement actually is another factor of omega. So in this limit, the enhancement is omega, here is omega squared, and so you expect a large enhancement that can signal the transition. Now, remember that we looked at some observables the other day that could, the energy of the ground state, show a change in the slope. The wave function obviously show that, but we cannot measure the wave function. And so we are looking for what would be the best observable to look at this transition, and we look at energy, and we look at the energy as a function of n, and we look at this difference between the pairs in the upper level and the lower level, and all of those show some signal of the transition. Now, energies, as you know, are very easily to be perturbed, and therefore, actually, a measurement of the wave function is perhaps, or closer to the wave function is even better. That's why transfer reactions are so important, in the same way like VOV2s. So one would envision a program where you do relative measurements and see indeed that the behavior is obtained, or here, and people have done that. I'll show you here an example of one of the nucleus that is considered a paradigm of a BCS, nucleus of superfluid, that is TIMS. We looked at them yesterday, and you can see when you look at the reaction of TP, so you transfer two nucleons into TIM1 18, you don't see anything really except the ground state. So all the intensity it goes to the ground state. There is, of course, some excitation at higher energy, but this is exactly what you would expect, and we'll show that in the problem this afternoon. All the strength goes into the ground state. Now, of course, you look at that, and the picture already tells you a lot. Then you have to analyze the data, and we'll try to see something if we do the DWBA today. Now, I wanted to show you this because that simple sketch that I showed there can actually be realized in a more sophisticated calculation here, where the strengths of the pairing transfer, this is done for a surface type of pairing interaction, follows exactly that in the thin region near the closed shell. starts to increase linearly, then in the mid-shell it approaches the BCS limit, then of course by symmetry goes down in 132 and increases again as you move up the shell at 82. So the sort of the hand-waving argument we just did is borne out by the more serious calculation. Theory also has developed considerably, and the group by Riccardo Broglia and collaborators in Milano have developed new codes that allows you to actually explain the cross-section in absolute terms. You don't need to fix any normalization. This result shows the data for those things that are, as you have said, the example of BCS, and these are the results of their calculation where the data is extremely well reproduced by the reaction code they developed that does not have any normalization whatsoever. Because here in this experiment that I showed before, the analysis that the group Alejandro Vierhard and people in the Copenhagen and Los Alamos, I think Rick was involved in some of these papers too when he was a young postdoc at that time.
I'm still young.
Yeah, you're still young, but you are not a postdoc, you're a young professor.
I would love to be a postdoc at my current salary.
Okay. And I would imagine, Rick, you can tell, I mean, this must be very exciting to be, I mean, when you saw this and, you know, so close to that time, I mean, very, very exciting. Not that we are not excited today, but it means, I mean, I could imagine real excitement there. Now, at that time, they had to actually make serious approximations in terms of the DWBA analysis, and this required a normalization factor that you could always argue, well, how do you know that you adjusted? So it was more like a relative measurement. But now there is no issue. You can do that in absolute terms. Now the only problem is that you have to contact Ricardo or Gregory because that code is not available for experimentalists like the other codes are. But nevertheless, the tools are there, and this is also very nice. Particularly when we go to the weakly bound region to make sure that there is no other effect in the reaction that may fool you. Again, PT and TP, we just said, are tools to gauge the ground state, and this again, along the lines of the example before, John and Sean Freeman and collaborators did the TP and PT reactions at Yale using the same targets in the experiments that I discussed before and analyzed the reactions. So here again you see nicely most of the strength except perhaps for germanium 74, which is not involved in any particular case here in the double beta decay, where there is some kind of fractionation of that strength. You see, it's a little bit going to the ground state, but a little bit going higher. That may be an indication of subshape coexistence there. But for the particular case of germanium and selenium 76, you see the dominant factor is a ground state to ground state transition, which again indicates that the ground states of these two nuclears seem to be well described with a simple BCS approximation, and it's up to the theorists to come up with a detailed, sophisticated calculations that are able to reproduce not only the occupancies that we saw before, but these cross sections that they determine. So I think maybe how are we doing? It's about time. Yeah. So this is a good time. I'll get back to another example, a recent example, somewhat recent example, and continue after coffee. Okay? Thank you. In this particular case, lithium-11 is only bound because pairing comes from the phonon picture on. You can take the NN interaction as we discussed earlier, and for this particular case, given the orbits that are involved, that particular NN is essentially negligible, and most of the pairing strength come from the low-lying phonon, in this particular case dipole and monopole and quadrupole modes, which are the low-lying phonons in lithium-9, are extremely important for that pairing correlation. And they claim that this is perhaps in nuclei the closest example of an isolated Cooper pair, which are the two nucleons which are in the halo state. And again, of course, transfer reactions will play an important role to confirm this picture of note, particularly that of the phonons, and therefore the experiment was done by using actually a PT reaction. Lithium-11 was produced in prime, and it was actually observed by a very clever device that was developed here in France, which is called Maya, and which is actually an active target system. So the target is the detector, makes it very efficient because after making the lithium-11 exotic nuclear and precious exotic residues, you better catch them all. And here you see some kinematic plots that relay the outgoing angles of the residues, the proton and the lithium-9, and those are the kinematic lines. You select those, you get the ground state and the excited state. Oops. Sorry. And with that type of statistics, you can derive nice cross-section, and that's when the picture of the phonon is borne out actually by, again, this absolute normalization that I mentioned earlier, and the coherent processes involving the PT reaction, and I'll show you here the results. Actually, they are very impressive to me. And if you were to assume symbol configurations of the levels involved, the S and the P, you can see that you don't actually see the data. You don't explain the data. You have to have a mixed configuration, and that mixed configuration, I'll show you later, seems to account rather well for both the ground state and the excited states. And look at the wave function that they determine. It's a nice mixed wave function driven by the phonon. There is a proton that is coupled to this interesting core of neutrons, which is made out of the simple core plus this coupling to the phonons, 1 minus the 2 plus, and of course the neutron amplitude is also mixed between the S and the P with a very small component of it. So the quality of the data, even in an exotic nuclei like lithium-11, is extremely good to tell you a lot about the wave function and the correlations that we find. So this actually was the last example that I have. I will now sort of continue with the topic of pairing, but we'll switch to another topic which we have not addressed, is that of neutron-proton pairing. I think you mentioned that during Pete's lectures, but not address that in detail. I will tell you a little bit. I cannot again address too much in this lecture, but I'll give you a little feeling of what the subject is, and this is a topic that you perhaps yourself become interested to work. So neutron-proton pairing. So I'm sure that you have seen this picture before in many ways or many forms. I felt that being in France, there was a better way to show the cartoon, so I composed this one. Sorry. Neutron-proton pairs. So, let's go back to this one actually. So essentially, the idea is as follows. We know that we have two types of particles and they can couple to a given isospin, as you have discussed that in detail in previous lectures. So you can have the so-called T=1 triplet, 2 neutrons, 2 protons, or a neutron and a proton coupled together to spin 0. And because of isospin invariance, which is a rather good symmetry, you would expect that those three components are on an equal footing, and I would not expect otherwise, that this should be there, particularly in N = C nuclei. Now we talked about the attraction of the neutron in the bare potential, but you could point out very quickly to me and say, well, you know, the neutron-neutron or the proton-proton are not bound. The only bound is the deuteron on the T=0 channel. And indeed it's true, and that's why you will have this other unique system, which is the T=0 component with spin 1. That will be the deuteron. And if I were naive enough, or not naive enough, actually quite so I could say, well, I would expect that along N = C, the main ingredient or the main pair should be deuterons. And if I want to describe my system as a BCS condensate of pairs, why shouldn't it be the deuteron and not these or those which we know are the main ingredients of the nucleus that we have discussed so far. So this is a very important question that with this renaissance of exotic states was asked again as what nuclei that are on the N = C line became available to study in more detail. And during the last decade, and mainly through spectroscopy work, a lot of things were addressing this question of what is the nature of pairing correlations in N = C nuclei. And the reason why N = C are very important is because as you move out of the N = C, it's easy to realize that because now the neutrons and protons occupy different orbits, really the spin 0 is not easy to do because the orbits are so different that you better be on an NN or PP system, and that's most of the nuclei that we have discussed so far are both superfluid in each of the species. At N = C, however, there is a possibility that the T=0 pairs, these sort of quasi-deuteron ingredients form. The Fermi energies are not the same by any means, but the orbits at the Fermi surface of each of those fluids are the same, and you can make these pairs. And again, we now can ask the similar questions that we asked before. If T=0 is present, how will it manifest? Will it be a BCS condensate in the form of a superfluid system? Will it be more like a pair vibrator, as we indicated in lead, for example? What is it, the nature of that? And this is a very interesting question, because this is actually unique to some extent to the nuclear system, given the fact that you have this possibility of coupling. Yes?
So the deuteron is only weakly bound though, right? So could you develop the same machinery for maybe alpha particles, since we know these are really nice discrete packets?
Yes, you can, and in fact people in the past have looked into that, and one of the conclusions that came out of those studies, again, is that in some light nuclear alpha clustering is important, but as you go heavier, and because of the spin orbit splitting, that's not necessarily the case. So for making a condensate of alpha particles, the best option you have is when you have a SU4. And which means complete symmetry, LS coupling. Now, as you heard yesterday, even in lithium analysis that you did with PIT, you have to put a splitting of the P3 half, P1 half, but still good enough. But as you go up, then the spin orbit takes over. And I think that is an interesting point that I will mention briefly, could be potentially one of the reasons why also the deuteron pairing does not develop, at least near the ground state. Okay? And here we talk about a deuteron, but with a little caveat. In the deuteron, the orbits involved are S. When we are talking about, say, nickel 56, we are talking about a deuteron made out of an F orbit, where the F are colliding in this direction, but making spin 1. So this is, I think, von Brentano would like to call that a quasi-deuteron. So indeed, this is a very active research, and by no means I think the answer seems to be clear. There's been a lot of controversy on whether it exists. I mean, initial evidence suggested that there was a condensate of T equals 0 quasi-deuteron, but then that evidence was revised. And so essentially, with all the material that you discuss in this school, probably the first one that you will say, Augusto told me about binding energy differences as a way to analyze pairing effects. So why not look at binding energy difference near N equals C and try to gauge whether there is a presence of the quasi-deuteron condensate is there. And indeed we did that, and it's not clear. What is clear from that analysis, though, is that the T equal 1 LP pair has to be there. And that one is not surprise to anybody, but at least the data from binding energy confirms that. Now, I mentioned the quasi-deuteron structure, and I don't know whether Norbert discussed that in his lecture, but nevertheless, the idea is that you have this structure, this quasi-deuteron, and you can look at the O-dot system, and indeed, the structure of the quasi-deuteron shows up, but the structure does the structure does not require some kind of a condensate, at least obviously, that jumps at you. Now, of course, the other thing we discussed with some length the other day, and Rick took it upon yesterday when we discussed the Nielsen model and gave you these details of the Coriolis force. If you have a quasi-deuteron, the effects of Coriolis you will expect will be a little different than if you have a normal pair. From the orbital angular momentum will be the same, but because those quasi-deuteron has spin 1, they will respond different than if you have a quasi-pair there which has spin 0. So people actually look for the so-called delay alignment That was the initial expectation, which I never really understood why, but nevertheless, people expected this backbending to happen later in N equals C nuclei, and actually reanalysis of that show that still the data will be consistent with the T equal 1. Now that doesn't mean that T equals 0 is not there, it means that you don't seem to need it explicitly, and if you would apply some kind of Occam ratios approach, if you don't need it, then it may not be there. I'm sure that you have discussed aspects of beta decay during the workshop. I don't know. Okay, beta decay, of course, can sense, particularly this transition. You go from a 0 plus to a 1 plus, which is driven by this quasi-deuteron, and you ask yourself, well, there is nice data by Andres Gadea and collaborators at GSI. Excuse me. That seems to be elusive at best, if you were to. I understand one of you is speaking. Very good. Are you involved in that? No? Okay, well, nevertheless, that's an interesting result. Still, I mean, this is only in gallium, so you have a lot of N equals C to study before put an end to the story. And I know some people, of course, from Sweden. Bo Siderwald showed very beautiful results in palladium 92, which I'm sure Pete probably have discussed with you. No. Okay. Where they have found evidence for a so-called spin-aligned neutron-proton coupling. I think a comments in order here, because I think part of the controversy and the criticism that came during the initial analysis we did, and still maybe lingering today, is, and you should be experts now, because the critical thing is the critical parameter, and the critical parameter has the same ingredients. The question is what the critical parameter is. Is it 1, less than 1, or greater than 1? It will be ridiculous to say that there is not equal 0 pairing matrix element. The only thing that we've been saying is that that matrix element, for reasons that we don't yet understand fully, is not enough to make the transition from x below 1 to x above 1. That's the only thing we are saying. And in this particular case, Bo Siderwald was a postdoc with us in Berkeley, so I love him dearly, but I think I disagree with the conclusion that this has to do anything to do with the condensation of neutron pairs. So, I mean, the first thing is that these are spin pairs, and there aren't very many of those, so you cannot make a condensate because they don't mix. It's only it's a very interesting state, but it's just one. But with transfer reactions 101 that we just heard before the coffee break, you will not be completely surprised if one will say that the smoking gun will be the transfer reactions. I guess that will be the tool where we can really probe these correlations of deuterons or not by doing transfer reaction. The question is which transfer reaction you do, and for that you have a little bit more choices than the ones that people have done for TP or PT, which are for the neutrons. And here we have several of those. The ones that I will pick as an initial step, particularly in the regime of radioactive beams, where these guys will be the target. So it's easy to make a proton, a deuteron target. It's not so easy to make an alpha target or a helium-3 target. And I will show you a little bit of how can you do that, of course. In the case of the P helium-3 or helium-3P, this will be sort of, if you like, the equivalent of the TP. you transfer isospin, 0 and 1.
Mhm.
But if you do any of those, you only transfer t equals 0. That doesn't mean that it's not good, but it's not as general. So if I have to pick, and given the fact of limited beam time and the fact that you may have only one shot, you better pick the one that you think is best. And for me, that's helium 3p. If you can do all of them, of course, you will do all of them. But I will show you an example of helium 3p. The idea goes as follows. You start with an even nucleus, that will be your beam. You transfer helium 3p and you transfer that empty pair, that could be a T equal 1 pair, or a deuteron-like pair, to both states of interest in the Orod system. And then the argument is that you measure the transfer cross-sections, and we argue, well, now today, as I said, probably I can calculate absolute term, but if you don't have that luxury, I can convince you that relative measurements already can be a signal of the difference between the two types of correlations. And so you measure both in absolute terms. Whether you can analyze those in absolute terms requires some normalization. The relative, the normalization will tend to cancel out the reaction aspect, because you see these states are very close in energy, and therefore the reaction part should be very close. And because we have a transfer of a L equals 0 pair, and I showed you early on that the transfer cross-section depends on the L of the composite particle that you transfer. This will correspond to a forward peak reaction. So you look at the protons in the forward angles, and that will be strongly sensitive to this pairing matrix. Pete already led the way in some of these estimates when he and others calculated deuteron transfer in N equals C on the basis of the IBM, and Pete did the calculations in the limits, and this is actually a sort of analytic solutions that you can derive, and you see if you are in the SU4 limit, that's a perfect symmetry. These two states we will populate it equally. If you go to the isoscalar limit, the T equal 1 yeah, so this one, in the isoscalar limit, when T equals 0 dominates, those are the deuterons, then you go to the T equals 0 state larger than you go to the other one, and vice versa. And you can also try to gauge that in a different approach. I give you this not because there are other ways. This is an IBM model. You can do a shell model calculation, and I show this in a simple model, toy model. I switch from a pure T equal 1 to a pure T equals 0, and X gives me that fraction. And if you see, this is the number of pairs of an even type. And one thing that you notice is that when X equals 1, indeed, the 0 plus pairs dominate. When you go to this limit, 1 and 2 dominate. And also know that the 7 plus, which is the high spin pair, they seem to be not very sensitive. And those are the pairs that are involved in palladium 92, although that's not an F. This is for titanium 44, so this is an F7.5, because that's the orbit that is involved there, which is the experiment that we did. Now, cross-sections for transfer reactions will depend on the number of those pairs to some extent, because you're transferring those. So that's the idea. It was certainly pointed out in some calculations by Peter Frovich early on that indeed neutron-proton pairing will influence the enhancement of deuteron transfer in the calculation for the reaction P helium-3 on argon 36. So I'll tell you a little bit of a experiment we did at Atlas to see if these ideas could be materialized. Of course, the transfer reaction, single transfer reaction have been done. I show you the case of Team 132 where they did DP. This is a little bit more challenging because cross sections for this are a little bit smaller, actually a factor of 10. So the question was, can we do this? And this is a sort of a cartoon depicting the type of setup that you will do. Beam is coming in. This was the target before, now is the beam. Then you imagine yourself having a helium-3 target. That's something that is not easy. And then you have a simple detector. And you see here, I put it at backward angles, and I'll show you why next, because I told you I'm going to measure forward protons. So why do you put backwards? That's it's a subtle detail. And then a neutron-proton pair is transferred to this guy, and then you do some kind of recoil detection to guarantee that this is the nucleus of interest, and at the same time look at that with the protons. Now, typical beams of this species are of about 1 million per second. Here at Ganil, for example, I'll show you an example. Again, this is the type of intensity that you need today to do this experiment. That's not much when you compare to stable beams, but it's not too bad because you can do also some other physics with particles if you just want to look at the discovery of an isotope. You can get by with maybe 1 or 2 a day. So, but these are challenging measurements, and this is what you need. And if you do that with some target material of about 100 micrograms per square centimeter, that's also not very thick, you will get something of the order of 20 counts a day. So a weak experiment, you get 100 counts, a 10% measurement. That's not too much. So it's challenging. And I'll show you that indeed that is the case. But hopefully there is a Spiral 2 coming up. There is FAIR in GSI, there is EFRI in the US, and of course Beacon now they are trying to develop low energy beams too. So some of these reactions should be possible higher than titanium-44. So this is a little picture of a setup that we did, very simple one. I'll show you the Ganil example later, and that tells you how it should be done. This was sort of like a proof of principle for us. I would, as I said before, once you make this exotic nuclei, you better have everything to catch them. Now, for us, this is the key element. This is a gas cell, so it's essentially a container that has very thin windows of titanium in both front and back, and then you just bring helium, could be helium-3, could be alphas in the form of helium-4, and then you cool it down to liquid nitrogen temperatures, and for those conditions, usually you get about 100 micrograms per square centimeter. That's not an unreasonable target. For those experimentalists who have been involved in sort of typical other reactions, for example, 1 milligram per square centimeter is not an unreasonable target too. So you're talking about not too bad. Now, those of you who are in the high energy regime, and if you go to Riken, you get a target which is like that, and this, of course, will be incomparable. So the luminosity there aspects are much better because of the target. You have other issues, of course, but nevertheless, here we go. The beam comes on this way. The cell comes down here and it's positioned in the center of the chamber. And then in this particular case, we have a device at Argonne called fragment mass analyzer that essentially tells you which is the final product. And you need that, as I will show next. Otherwise, the reactions that happen in the window of the cell overcome the protons that you want to detect. Yes?
Yeah, I was just wondering why you were pointing out the thickness of the target compared to RIKEN, for example, because RIKEN or GSI have much higher energy.
Correct. No, I was saying that for those of you who are more used to RIKEN and you use this target, you would say, what? 100 million?
Yeah, but you can transfer.
Of course, that's what I said. You can do knockout and learn similar things, but for this particular type of physics, there is nothing like particle spectroscopy at Coulomb barrier energies. So that's why these facilities will have in their plans, I think Spiral 2 is already in that regime, but RIKEN, FAIR, and FRIB will have to slow down the beams and provide the near barrier energies. Simple kinematics, you go back to your classical mechanics program, and then you do this, and then you find an interesting thing, of course, is that with such a reverse kinematic where the target really now is the beam, very heavy on a proton target or a light target, they cannot go too much forward than 3 degrees in this case. That's the recoil. So the recoil in this case, which is scandium 42 for that example, will be focused 3 degrees, and then you can catch that in a forward detector that tells you, yes, it was scandium 42. Because you can have one proton transfer or one, anything can go out, you know, could be other species, but we are interested in scandium 42. Now the protons have an interesting thing because of the Q value. It turns out that the protons that go backward in the lab frame, they are forward in the center of mass. And those are the protons that I'm interested in because those are the L equals 0 transfer. And therefore, if I put my detector in the backward energy, in the backward hemisphere, I will have a very clean setup because there aren't very many protons or other particles that can go backward, except obviously the evaporation one, and that's why I need the recoil. And the energies of those protons are about 5 to 6 MeV. Nice range for a nice particle detector. And because actually there is no other particle going backward, then you don't even need a telescope. You just have a detector. If the detector detects something, it has to be a proton, nothing else. So, this is something that you can actually, if you are interested, I have a code that this gives you that I didn't distribute, but if you're interested, I can give you again. It's a Fortran code that does the kinematics, but that's something that most of you must have. So what do you get?
Sir, so in previous slide,
Yes.
there can be possibility that this 3 helium can transfer a deuteron and put in a deuteron in the backward side and transfer one neutron to that target nucleus.
Yeah, it could be a helium-3n, of course, reaction, and but then that's why I say then you have the forward protons, if you like, which are backward. They go together with a recoil at forward angles,
Right.
and that in this particular case, the FMA, you can put your own device. An ionization chamber will tell you whether it was scandium or not. Yes. You can do helium-3D. The D could, if you do the Q value, will not reach. And here, if you didn't have that detector in the front of the recoil, then you see the blue spectrum. And then although you can see here some lines, because this is actually a stable beam where we tested the device, this is silicon, but you see that there is a lot of protons in a structureless spectrum due to the evaporation. So here, silicon comes in, it hits the titanium in the window, it makes some kind of compound nucleus that is excited, decays by particle emission. Some of those are protons, and that's the blue background here. When you look at the coincidence between the silicon detector and the FMA, you see nice coincidences, and these are dominated by the protons, which you see now here once you gauge on this, because these are the protons, the recoil actually doesn't make it really to the FMA or the forward recoil, because they are distributed over a large range of angles. So you do that, you select your scandium 42 after you put that, and then you see nice energies. This is the energy of the proton in tens of keV, so about 5-6 MeV. And of course, the lines here, as you see, they bend over because there is a little bit of kinematics. The angle the proton comes out changes the energy, and it's easy for you to correct that and project this. And you see nicely the 0+, the 1+, and some other states. So we did that, and of course we wanted to compare, because this has been measured before. Calcium 40 is a difficult target, but it's not impossible to do. And people have done this measurement before in the early, in the 70s. And then you see here, these are the results from those experiments done in normal kinematics, and these are our results. Cross-section and ratio of cross-section agree very well with previous measurements. So that gave us confidence that we could do the experiment. Now the question was, will we have enough of a beam to actually do the experiment? And that was something that was yet to be seen. Other examples, we also did argon 36, sulfur 32. You see nice spectra. Although the resolution, those of you who are experimentalists and may be involved in some of these experiments, is not great. That's because of the target, the gas cell has a width, and also the protons are coming out at different angles, so it's not the best in terms of energy resolution, and also because there is a compression due to the fact that you are looking at backward. The energy of the different states get compressed, and they are closer together. So in some of these cases, as I will show you later with the Ganil example, you need to improve on that resolution by using germanium detectors. So germanium detectors still to the rescue, even in a particle spectroscopy experiment. Yeah, this is interesting. You may ask, how did we do the titanium-44? Of course, titanium-44 is a radioactive nucleus. It actually lives 60 years. And so what we actually thought was, well, why don't we do it offline? It was cheaper than actually trying to make in a direct mode. So we bought titanium-44 from Los Alamos at a price of about 20K and 100 microcuries. Now we did a little bit of nuclear chemistry there. John Green from Argonne helped us do that. We had to actually transform the titanium from the form it came, is sitting there, into the form that it can go to a tandem cone that was used to produce the beam, and it has to, we did some chemistry, and at the end of the day, all that titanium that came in was put in a cone, which is shown there, mixed with just natural titanium, and then the accelerator selected titanium-44. They work, yes, you can see here, this is spectrum of a monitor at 0 degree, and actually you can see both titanium-44, and which is the nicely here the largest peak, and this is calcium-44, which is also present out of the machine. And this is another reason why you need the detector at the back, because if you didn't have that, you will have reactions coming from calcium-44, and those are interesting perhaps, but not what we are after. So you need to be able to gate on the back and require that it's scandium-44.
But sir, why you mix this 44 titanium with normal one? Because you have English target, so why you mix that?
Oh, that's to actually, because the 100 microcurries of titanium-44 is not big. It's very little. You have to mix that in another mixture so you can have that material in a pellet.
Okay, but
It's so little that you cannot have it. I mean, you will not even be able to see it. So you mix a little liquid there, you put it there, you mix it with other stuff, because that it goes into this. You have a tandem in Calcutta, or no, it's a cyclotron. So in a tandem, you have a sputtering source. So you come with electron, you hit a cone where it has the material, and then that gets evaporated, if you like, and then transported to the machine. And you need to have some material there, and the way you do it, you mix it with normal titanium, for which you do the same chemistry, you know.
How much is it in gram, or milligram, or microgram?
Oh, that was something like less than a milligram.
20 k by milligram.
It's very small. It actually comes in a solution, because what they do is they make an installation of protons at Los Alamos, then they do some chemistry, and all that is due through some wet chemistry, and they have it in a Tickle form, which is titanium chloride. And that's why the tandem doesn't like the titanium chloride, it needs a solid. So it has to be reduced into oxide. So way beyond my chemistry. But John. So here you see again, this is a little bit more detailed. You have an ionization chamber, and you know the delta E is proportional to Z. There you see clearly the titanium-44. And again, when we do the settings corresponding to our titanium-44, you see that indeed it is the strongest product, but there is a little bit of the remnants from the other products. But we are confident that that we had a good selection, and the key question was how much we were making. And at the end of the day, when we ran for 4 days or so, 3 days probably of real beam time, we obtained about 10 to the 5, so a little bit of, so half of what we thought we could do of the million per second. But that was enough to see something, and I'll show you what we saw. This is to convince you that we have that under control. If I look at the energy that we measure for those, you see that these are the angles covered by the detector, and these should be the energies that we see. And actually, when you look at the spectrum, and you gate on vanadium-46, that's our NP transfer from titanium-44 into vanadium-46. You gate there, and you see with some, the expert eye, maybe if you look at it a little bit like that, you see some lines popping up there. These are the lines of the proton groups. Now you can, of course, project this once you correct by the energy, and you get a more promising spectrum that's there. And as you see, that's why it's so challenging. This is at the limits of what you can do, and this is one of the reasons actually why we're still trying to convince ourselves that there is no issue with the data and that we have everything under control. But you notice already one clear thing is the following. This is the ground state, that's the 0 plus, and then this little group there, you cannot resolve. It could either be a 1 plus, a 2 plus, a 3 plus. They are lying very close together. We cannot resolve that. But the ratio seems to be in favor of the 0 plus, similar, if you like, to other cases of TP. The only difference here is that you see some other structures. This is not the strongest peak in the bunch, isn't it? And so we're trying to figure out what those are, and that's why this is challenging. This is one of the areas where I'm sure those of you in the experimental groups may be interested to development of new detectors, new techniques, something that will be probably one of the major areas of research in radioactive beams, because this is an interesting answer, and still you can see we are at the beginning. And this is only titanium-44, which is not too far from calcium-4. So I think here's a lot of things to be possible.
Excuse me,
Yes,
I have a really simple question.
please.
Well, if that small peak is a peak,
This one.
this one, so what about the other one? So the
That's-
other one cannot be a peak either, so,
Oh yeah. This
No,
this clearly is a
but
peak.
what about those then in the middle?
Oh yeah, they could be. I mean,
Those two, so those
this
are,
and that.
no, in the middle,
This?
yeah, this one.
No, that's difficult. I mean, it's only one count in one channel. Usually there is a resolution, so you would expect the peak to have some fatness to
Okay,
it. Now, of course, there could be, but with the statistics we cannot rule it out. But I think here what we are interested in really, the main goal is really looking at the L equals 0 low-lying state, but we need to understand what that is. And I have an explanation, and that's something that again may take some time to discuss, but so that's a good point to make. So actually this was seen in the calcium isotope when people did TP. So we talked about transfer reaction of a triton, where you either put the particle into the nucleus or you take it out in a PT reaction. So in a triton or a helium-3p, that pair is in a relative state of angular momentum 0. And we said that these objects in the nucleus you go in or come out of it, those are not S orbits, those are high angular momentum orbits which are coupled to spin 0. So you have to ask yourself, what is the probability that you can find out of that F orbit, say, an S1 pair? And the answer is not obvious, but it's not unreasonable. The larger the angular momentum is, the more difficult it is. If you start with an S orbit, then it's almost 1. But if you start with an F7.5, it's not as 1. And it goes down very fast. And you see here the speculation based on what they've done in the calciums is that the p orbit comes into play, and although it's higher in energy because the p is above the f, the cross section is larger because making an S1 pair out of the p3.5 is much easier by almost an order of magnitude in cross. So that's why we believe these peaks are so large. It's not because the strength is large, it's because the cross section due to that overlap with the triton or the helium-3 slabs. When you normalize this with the WBA calculation that takes into account that formation factor, the strength goes down, and the only one left is this. Well, this one too, but again, smaller. For this is the same. And that's something that people, I believe Rick told me the other day, you guys used to call this the hot orbits or something like that, huh?
Yeah, that was mostly in heavier nuclei, but yeah.
But it's exactly the same. I mean, this low spin, they are already naturally in this low relative angular momentum, and it's easy to put it or take it out. That's why. Now, of course, we are not the only ones that would like to do this, and in fact, there is a strong program here in France. And actually, this experiment just ran in April. Were you involved? You were still in Japan at that time. Okay. I was supposed to come here to that experiment, but unfortunately, United canceled the flight 2 times, and I couldn't. So, but nevertheless, they ran and look at the way they did it. This is the thesis work of Benjamin and Marlena C. and Yorick Blumenfeld are the leaders of but it involves a long collaboration of many people, because as you see, the setup is really, really done professionally. This is more than just a proof of principle. It has all the artillery that you may need. You have the target. In this case, they use, in this particular case, they picked the reaction to do. They did P helium-3 and D alpha, so they actually doing both reactions, the T equals 0 and the T equal 1, T equals 0 combination. They have about 10 to the 5 particles per second. They went for nickel 56, but they have a large coverage, which includes the detectors for particle, which are the so-called tiara and mast. They have the separator here at the front. Here they don't have, you see, a magnetic separator that the FMA. They have just a detector to select the products. They have some monitoring for the beam to make sure that it's centered in your target. And as I said earlier, in this case, as you will see, the particle resolution is not good enough, so you need the help of some gamma ray detectors in the form of exogam. Some of the kinematics again here. For the P helium-3 is not so clean as the helium-3P, so that they need a telescope. This is the actual centering of the beam in the target device with that so-called CATS device. Then once that's done properly, you know that you are doing a good job in the focusing. Then you have beautiful discrimination of the different channels, because now this is forward too, so a lot of particles come out, and then you select your particle of interest in either the helium-3 or the alpha, depending on the target. The interesting thing is that they have also the triton, so there you have the isospin symmetric reaction in the same data. You can do P helium-3 or PT, and the T equal 1 channel should be the same for those. So it's a very nice confirmation. So beautiful data set, but still not enough to do the complete job. So then you have exogam, where you have to look at some of the gamma lines in nickel 56, that's the level scheme, and you see there is a very low line stay there, and so here you have the power of the gamma ray that has much better resolution to resolve some of those states. Of course, a gamma ray from the cannot tell you the ground state, but it allows you to correct for the feeling. So they have a nice setup. Of course, the analysis is ongoing, but it takes some time, and I'm very excited about what they can can see here the nickel 56. Yes.
The telescope spectra, so delta E versus E. Did you cut the background yourself because it looks like textbook spectra?
I didn't. If they did, I don't know. I'm sure that's very nice. I mean, why should it be?
Too nice, even.
Why would you mean too nice? I mean, it's a very clean.
So what background do you have? So the uncorrelated events which you come from time, that is taken care of.
Okay.
They are calibrated, so the resolution is very, very good. Because you don't
Now, remember that contrary to what we had before, if you were confused maybe with the statement that I made from our run, this is much more complicated and detailed setup. This background here shows up because we don't have a delta E, but if we were to have a delta E, the protons will be in the same banana. But there they are not of interest, but as you can see, when you, as Navin says, when you put the prompt coincidence, then they go away. So it's that inherently clean. If your beam is clean, and there is no background, which you shouldn't, for charged particles, they should be rather clean. So I think the question now, of course, as I said, a lot of people, including yourself, may like to get involved in this, and so in order to project a little bit of what you may like to see, I made for you a plot here where I took some estimates of what beams may become available, and one of those are already here, as we saw even if Spiral 2 is not there, we saw that already nickel 56 out of Ganil is already at that level, and with the upgrades you should be able to excurse into even mass 80 region. Now I have 3 levels of experimental. The simple setup that I show you just as a reference, I don't think people will use. You have more important and powerful devices now, and I would not call the Ganil setup a simple setup. Then you have devices like a solenoid spectrometer, which has been developed by Atlas, where you have high efficiency and an improved resolving power because it does not compress. It decompresses the kinematic compression due to the reverse kinematics. But moreover, I think you have the device like Maya type of device where your active target is not only the detector giving you large efficiency, but it's also the detector, so you can have everything coming out of the reaction. And for those, I did some estimate based on the specifications of the device at MSU. We may be able to go down to something like 1,000 per second, optimistically. So if you take yourself sort of like in between for FRIF or Urisol, we should be able to get into the region of mass 90. I think T100 will never be possible, at least for a while, until there are some increases in the beam production. So this is sort of the landscape for this particular physics case, and this is a subject that probably those, as I said, there is still a lot to be done in the experimental side, but also on the theory side to try to understand what's going on with this elusive mode. And so we are approaching actually the end. I'm a little bit ahead of time here. That probably is not unwelcome.
Can I ask about this Ganil experiment?
Yes.
Didn't they do a second? This was what you showed was.
This they, as far as I yes.
Right?
So when we discuss with them, I believe they also did the next one up from titanium. So they did chromium 48. But I don't. Marlene sent me this but I didn't ask about. I think they run also chromium 48. So you have calcium 40. Then the next even is titanium 44, chromium 48, and then you go into nickel 56, iron in between. So I believe, oh, maybe they did iron. Sorry, iron. So they didn't do chromium.
The chromium was in the proposal.
Yeah, chromium, that's the one that I suggested they do, because it meets shell, that's where you would expect the maximum effect, but I see.
There was some technical problem.
They couldn't get chromium. Okay, very good. Iron, there it is. This will be a fantastic data set. I'm really looking forward to see some of the results. And nickel 56 actually is very interesting, because there you know that probably the way they develop are phonons. You see, both channels will be phonons, T equals 0 and T equals 1. It will be very nice to see how those phonons, if they are what are the properties of those. Okay, so we have, so a few odds and ends on the topic of pairing, and I think then we conclude a little earlier. So we talked about pairing. We know the analogy to superconductors in solid state. Of course, temperature is a degree of freedom that we can also control to some extent in the nucleus. That is measured by the excitation energy. So we can look at the properties of pairing at excitation energies. And actually, because of the picture that Rick showed you earlier today related to the level density in the even nucleus, you see that in the even nucleus there is a gap naturally formed by the pairing correlation, and then level density starts to increase. So there is some kind of a dead region where there is no level density, and you can study the dependence of level density with excitation energy, again, by using some reactions. This has been led by the Oslo group. And this particular paper analyzes those level densities, and they conclude from that analysis that actually at a critical temperature, which they determine from the level density data, they correlate that to be about 0.7 delta. This number is very close to the BCS value for the critical temperature. So they determine by that analysis that at that temperature the pairing gap is gone. So I think that is an interesting confirmation, if you like, of the picture of pairing correlation in another layer. So we saw binding energy, we saw rotational properties, and it should be in temperature too, and long and behold is there. But again, this is not this is a more recent topic, because the techniques that the Oslo group developed are now being applied to really study level density in more detail than it was addressed before, and particular because some of these level densities are low photon energy, has strong implications for astrophysics, because N-gamma reactions will come from, we sense that level density and may get out of the path by emitting a gamma. So there is an important aspect there that many of you may be interested to look into. The analogy to the shape degrees of freedom can be taken even further. And you are familiar with the fact that you have giant resonances in shape, like giant quadrupole. There is, of course, the giant dipole, but that will be not equivalent to this particular mode. The one that we are more interested in for analogy will be the quadrupole. And those involve microscopically excitations that involve the next shell. And so we have the lower shell here, and there is one state that comes down. That's the pairing vibration, say in lead 208. But what happens, pairing should be there also in the upper shell, and there should be an upper shell collective state that comes down in the same way that a giant quadrupole becomes collective. That state will be collective, in fact as collective as the ground state to some extent. And the question is, can we see it? Now, in spite of many experimental efforts, that state has not been seen yet, and it's an interesting question to answer. Why? Some of us have been thinking about doing experiments because some people argue that the TP reaction, which is the one that you will use to come and dump the two neutrons in this region, is not necessarily the right tool because there is a Q-value mismatch that is not favorable. And the reason we haven't seen it maybe is not because it's not there, it's because we cannot make it. So people like Lorenzo Fortunato and Andrea Vituri have come up with a suggestion that maybe one could use helium-6. And for that one, it turns out that the Q value puts you right there in the region of the giant pairing vibration. There is a problem with data using helium-6 because helium-6 likes to break up emitting two neutrons, and so the analysis of the data is not clear. I have some ideas, and maybe you guys can come up with some ideas. And there is also some addressing that, is that the open quantum system, as you become weakly bound, you start to see the continuum. And I want to show you this plot by Jacek, Towaczewski, and others. I find it extremely provocative because you see here, I think it will take me back to Mottelson's quantality parameter, which we started the other day. And in normal nuclei, when we start in the shell model description, he argued that the quantality parameter naturally gives rise to a mean field. You have a Fermi surface, and your binding is determined by the Fermi surface, essentially by lambda. Now you imagine as we climb into the binding surface, at some point the system becomes weakly bound. This is the threshold, the ground state shoots up, and at some point lambda becomes close to 0. In such a thing, this picture doesn't hold anymore, because really the binding is lambda plus the gap. And if lambda goes to 0, then your picture is now dominated by the two-body correlation. There is no mean field even. The concept of mean field may not be even there. So that opens up interesting questions of when you are here, and perhaps the best example of this is lithium-11. We saw that the binding in lithium-11 was really all given by delta through the form. The question is, what do we expect? Will pairing dominate? What are the properties of this pairing system near the threshold? And as you see and indicated here, the more weakly bound you bound to touch the process nuclei, which are extremely relevant for nucleosynthesis, and then their properties indeed will be reflected in the astrophysics scenario. So I think this is a very interesting aspect. Experimentally, I'm very interested to address some of these questions, and those of you who are theorists, I will encourage you to think about that too. With weakly bound system also, other effects beyond, for example, Borromean system, you have heard about Efimov states. Calcium-60, for example, is thought of the system where Efimov physics may come of interest. So a lot of interesting questions that are there for you. Yeah.
I was wondering if there is any kind of experiment where we can treat the same kind of problems, but now for the four nuclei. I mean, in order to get a kind of correlations, but now with quadruple interaction or something like that.
Sure, I mean, you know, we didn't have time to discuss this in these lectures, but for example, one of the nucleus that is accessible at RIKEN today, near the drip line, is magnesium 40. Magnesium 40, which you would have expected perhaps to be a closed shell nucleus on the neutrons, at least for n equals 28, is actually a very interesting beast. It's a mixture of prolate and oblate round state, for which all what we are discussing will be applicable. So that's a region where weakly bound system, deformed halos, Ikuku Hamamoto has pointed that out, you know, neon, magnesium, knockout reactions, whether you know, if the core is deformed but you have a weakly now, then the tool to analyze that is Nielsen in a weakly bound system. Now, you cannot do it with the code that Rick gave you because that doesn't have weakly bound. That's correct, it's an harmonic oscillator. There you have to use a Wood suction. And then the orbits will bend with binding. Those are the important orbits that will play a role. So yes, that could be done. And it's very interesting. It's one of the topics where people are addressing at RIKEN now and MSU here too. I think we were chatting with Olivier Sorlan the other day in nuclear structure. They are doing some measurements in fluorine where they're looking at the residual interaction in when you know the two nucleon are unbound, see whether there is a change, because we don't know that all those little discussions we have about residual interaction may not carry all the way through. Is it really the volume? That's something that you can check, because if the volume you're bigger, they should interact less, but there are more of those continuous states. So, okay. Very interesting. Open quantum system, open questions for you. So I think this is very exciting, and I think this is about the end of the lecture. So yes, let me conclude with a little bit of a sort of a projection here. I will be extremely disappointed. Oh no, there is one more. Yeah, sorry. So this is more like a speculation, you see, because this is nuclear matter. This was done, you can look at those two papers, but I find this plot very, very exciting, because here what they show is the correlation length versus the separation of the Cooper pair in nuclear matter as a function of density. And for normal nuclear matter, which will be here, you see that the correlation length of the Cooper pair is much larger than the separation. This is exactly what happens in superconducting. The correlation length of the Cooper pair is large. In fact, in superconductor, it's really large, much larger than the size of the atomic structure. Now here we are bound by the size of the nucleus, so it cannot be much larger than the size of the nucleus. But nevertheless, the picture that emerges is one where the Cooper pair is sort of an extended, so this guy is here, the other one is there, but they talk to each other. They know it's like sort of Fred Astaire dancing in a floor where they are far away, but they know what they're doing. They are correlated. And it's a long, the correlation length is long, much larger than compared to the distance. But there is a region here where the density becomes, say, 10% of the normal density, where it flips over. The pair correlation is smaller than the distance. So here, this is more like the Bose-Einstein condensate. This is more like the PCS condensate. So now, are we going to see regions in nuclei, finite nuclei, where the density is so low? Well, why not? The surface where pairing dominates may be weakly bound, and then it will be low densities. So speculation, yes, but exciting speculation. That's where we may be interesting to focus. And in fact, Matsuo has done recent calculations that some of these effects, although not as strong as this, may be already happening beyond T132. And two neutron transfer reactions in those nuclei will be of extreme interest. However, unfortunately, there is not much T132 to those experiments now, but we should have them in the near future. And the question again, from the two neutron transfer reaction is what do we expect? For example, if this is the real nature of the condensate, I would expect that the cross-section will shoot up immediately, because it's already had the shape of the pair in the trigon from pair. So this is very interesting. Now, again, this is nuclear matter, and of course neutron matter. These are effects that apply to astrophysics too. So I think this is really the last one, and so then I will then conclude here. And as I was saying, there are some experiments here that you can extend this in the future. Hopefully you will be involved with those. Some of those who are maybe becoming more available in the near future will be to do this, maybe nickel 78 too, which is another closure of interest. As I said, you will need tritium. There is no tritium beams that anymore to some extent, unfortunately, but you can load foils with tritium, or you can load a cell with tritium. That's about a Curie, so it's not so unreasonable that you can do that. So I think with that, we conclude the physics, and as I said, I will be very unhappy if the scene portrayed in this cartoon happens to any one of you. I hope that in these two lectures I was able to convey some of the excitement and take you out of that possible scenario. And I hope that you had as much fun as I did in preparing the lectures. I think it was really good for me to prepare that. We have more activities tonight, and so as a conclusion, I will give you my forecast, but it's always difficult, you know, in this world you have to learn from your giants in the field and other fields. To predict the future is very difficult, Bohr said, so I will not doubt that he's right. And then, actually, these days with shrinking budgets and difficult issues that we face in order to convince our funding agency, future is not what it used to be. But nevertheless, I think the forecast is sunny and warm for us in nuclear physics, and I encourage you to follow that. And with that, Alain, merci beaucoup and best wishes to you all. It was nice to meet you. Thanks.